Light and day is more than you'll say, 'cause all my feelings are more than I can let by or not, more than you've got. Just follow the day, follow the day and reach for the sun. You don't see me flying to the red one more your love. Just follow the seasons and find the tide. Reach for the bright side. You don't see me flying to the red one more your love. Just follow the day, follow the day and reach for the sun. Just follow the day, follow the day and reach for the sun. You don't see me flying to the red one more your love. Just follow the seasons and find the time. Reach for the bright side. You don't see me flying to the red one more your love. Just follow the day, follow the day and reach for the sun. Just follow the day, follow the day and reach for the sun. Just follow the day, follow the day and reach for the sun.
All right, so we'll start on the next topic, which is module, I think, 3 at this point. Or maybe it's 4, I forget. Basics then is 1, then, or yeah, whatever it is. It's 3 or 4. And the topic for this is loops, right? Because you do need to repeat things over and over a lot of time. For example, if you have a lot of data and you want to do an operation on that data, you need to iterate through that data and do the same operation on each one of those things. And so a loop control structure is your go-to to do that kind of repetition. You don't just copy paste the same code 5 times, because that means you will only ever have 5 pieces of data, right? Instead, you write a loop to do it for as many pieces of data as you have at that moment in your program, which you may not even know when you're writing the program or compiling it. For every loop, there are 4 basic elements for that control structure. Right? If you're going to do a loop, right, you got to start somewhere, and that's our initialization statement. Because if you're going to run around the track, 50 times or whatever, you got to start somewhere, right? Then you have a continuation condition. The continuation condition says that you should keep going. Or the opposite of that, the termination condition, is when you break out of the loop and you stop the loop. Because if you want to run 50 laps, how do you know that you got to 50 laps? When you get to 50 laps, you stop, right? And then finally, of course, you do need to make progress towards that termination condition. using an increment or update statement that makes that progress, right? First lap, second lap, third lap, etc. And then finally, the fourth one that is usually not part of the loop discussion is you're actually doing something in the loop, right? And so I include the loop body in this because that is the fourth element. The loop would be useless if you just looped around and you counted to 10 and did nothing, right? And so you do need a loop body, something that you're actually doing inside of the loop that gets repeated. Let's go ahead and give us some more room there, okay? All right, we're going to look at two different types of loop control structures for both languages. And again, we're not to the point where the languages start to diverge greatly. So the same syntax is going to be applicable to both of these languages. We're going to look at for loops and while loops. There are other types of loops, do while loops. We're not going to cover those. And then there are enhanced for loops, but only in Java, and that's where we kind of start to diverge. So let's go ahead and start with for loops. And note there that I have stylized the for because that is a keyword in both languages, right? And we call them for loops because they use the keyword for, right? All three of the loop elements are on the same line. That is the initialization, the continuation, and the increment. So I'm just going to go ahead and jump into a code mode here and write a loop that counts, say, to 10, right? So for int I equals 0, right? There's our initialization. Let me move that up so you can see it. This is our initialization. Where are we going to start? We're going to start I at 0, right? Here's my continuation. While I is less than 10, strictly less than 10, semicolon, I++. We'll talk about that syntax here in a moment, but all that does is it just fancily adds 1 to the variable I. And I'm not going to do anything in the loop body, but we do have a loop body here with an opening curly bracket and a closing curly bracket. I'm not going to do anything other than just simply print out the value of I, right, and the line, right? So there's my first for loop. Again, the first three items, the initialization, the continuation, and then the increment is all done on the same line. Before we actually see this in action, let's go ahead and make some observations about the style and the syntax, right? So style, right? Opening bracket is on the same line. Closing bracket is aligned with the F in for, right? Everything is indented. In fact, let's go ahead and split these out. Opening bracket is on the same line. The closing bracket is aligned with the F and the for. The loop body is indented, just like we did with if-else-if statements, right? What else do you notice about the style? Not the syntax necessarily, but the spacing, right? No space between for and the opening bracket, or the opening parenthesis, etc. And then we've got the parenthesis at the end. What observations do we want to make about the syntax, though, right? These are the things that have to be there, right? Both the initialization and continuation are ended with semicolons, right? That's kind of weird that the third one is not. The increment statement does not have a semicolon. Right? Why? I think it's inconsistent as well, right? And especially because this thing right here is a logical statement. When we wrote our if statements, did we put a semicolon at the end of the if statement? No. In fact, that was a syntax error. But here we are. I++, where it adds 1 to I, that is an executable statement because it does something, but it's not ended with a semicolon. Don't ask me, I didn't write it. Right? Somebody wrote it 30 years before I was born and we're still stuck with it. Every language does it like this that is a C-style syntax. I do believe that it's wrong and inconsistent as well, but that's what we live with, right? All right. So what else do we see here? Other items. I++ is the increment operator. It adds 1 to the variable I. Increment. All right, there we go. Increment operator. It adds 1 to the variable I. We'll look at that here in a moment, but just know that it's syntactic sugar, right? We like sugar because it tastes good, right? It makes our language more rich and robust. And so they've added this increment operator because adding one to a variable is so common that they just added it as part of the language using this shortened syntax here. All right, well, let's go ahead and run this thing over here in, say, C. Right? And let me go ahead and tab it over so that it's all nicely aligned. Right? GCC. Oops. Lecture CSC1. All right, GCC demo. Now, before I do this, you tell me, what is it going to end up printing? Let's walk through it, at least initially. Yeah, go ahead.
It's going to print 1 through 0 through 9.
0 through 9. Why 0? Why do we start at 0? Because that's our initialization, right? Is 0 less than 10 strictly? Yes. So we jump into this loop and we print it out, which is 0, right? Here, I'll hold it up in my hand right now. 0. All right. And then what happens at the end of the loop is that we add 1 to it. Right? So now it's 1. We come back up here. The initialization is only ever done once at the beginning of the loop. So we go back up here to the continuation. Is I still strictly less than 10? Yep. So we execute this, it prints 1. I plus plus. Now it's 2, 3, 4, 5, 6, 7, 8, 9. 9 gets printed, right? Because 9 is strictly less than 10. What happens now? 9 goes to 10. Now I need 2 hands to do that. So is 10 strictly less than 10? Nope. So what's the last thing that gets printed? 9, and then it's done. 0 through 9. You can change this, of course. You can change this so you start at 1. What will it print now? 1 to 9. Right? Right. You can change this so that it's less than or equal to 10. What will it print now? 1 through 10. I'm going to go ahead and move it back because this is what we call an idiomatic for loop. Eventually, we're going to be using loops to iterate over data stored in arrays. Arrays start at 0. So this is going to be a loop that you are going to write 1 billion times in your careers if you write code, right? You are going to write for loops that start at 0, go up to some variable, n, where you can put that variable n into a value here, 10 here, right? So it doesn't have to be hard-coded here. In fact, it usually isn't because you don't know how much data is in there. I just have n elements. Right? Another question here, why did I use I? It's not imaginary. It's an integer, sure. Say what?
Interval.
It's an integral, okay.
Interval.
Interval. Sorry, interval. Okay, interval, all right. Increment. It's short, right? All of these are good arguments. It's also used as an index, right? So I is usually used, right? So other items, I, and then, of course we can use J, and then of course we can use K, are typically used as increment variables, right? And for all those reasons, it's short, stands for index, stands for increment, stands for interval, right? Whatever other I's you can think about here. And why do we use J and K afterwards if we've already used I? I, J, K, right? Alpha, it's just A, B, C, right? We're not getting creative here, right? We don't want to be creative. We want our code to be readable, right? That's preferred. So let's go ahead and take a look at this idiomatic for loop in one other way, right? I'll do it like this, okay? So this is a Python tutor, even though we're not learning Python. It is a code visualization tool that can be used for many different languages. In this case, I'm using it for C. Let's go ahead and visualize this execution. You can run your own code if you want to understand it a little bit more and see what's happening in the background. What you can do is you can walk through this step by step. So for example, if we go to the next step on step 5, you see n over here is in the stack. There's a heap. We'll talk about those later. Right? And it receives a value of 10. And now at line 6, did you see that a new variable was born? Right? If I go back, you see that I doesn't exist. Why? Because it's declared on line 6. It was born on line 6. Okay? And now let's go through iteration by iteration. Right? Initializes it to 0. And since 0 is less than 10, it gets printed out. Goes back up and increments to 1, right? That's not great because I++ actually happens at the end of the loop. right? And then it comes back up and sees that it's still less than 10, next, right? And so you can see what your code looks like and stop it and pause it and run back and forth if you want to. Go back and forth on each one of these steps, right? So that's why it's running 0 through 9, right? So the behavior, some observations there. The initialization is only executed once before the loop, right? The update, right, that is the increment, it happens at the end of the loop, right? The continuation check is evaluated at the start of each loop, right? If it is true, the loop executes at least one more time. If it is false, then the loop terminates. And normal control flow, right, linear control flow continues, right? Because I had other stuff in my program. In particular, I think I said print the end, done or something like that, right? So that's the behavior of our for loops. Now let's look at that new syntactic. Oh yeah, go ahead.
I feel like one thing you forgot to point out is what happens to the variable after the for.
Good. We'll talk about a scope here in a second. Yeah, if you want to go back in time to the 1980s, you were not even allowed to do this in C. You had to scope your variables to the top. All right. So first of all, let's go ahead and get rid of, as a preview to scope, let's go ahead and get rid of that declaration right there. Is this even going to compile? No, because did you declare I? You can't use a variable before you use it, so it's not going to work. Now I declared it right here, meaning that it is scoped. Right, scope. You're looking through the submarine scope, and you can only see variable what you see right there. Right. Just a second. After the loop here, can I print it out? Right. There we go. Let's see if this compiles now. Nope. It was born. I was born on line 13. It dies on line 16. It goes out of scope on line 16. So consequently, I does not exist anymore. We can't do that. Unless I go back to the 1980s and declare it right here. Right? And now I can't declare it twice. You can, but now you'll have two variables of I with different scopes, so be careful. And we're not going to get into that because it's way too confusing. So let me go ahead and execute this now. Now remember that this loop is going to execute 0 through 9. Tell me what the value will be on line 17 when it gets printed. In fact, let me give it a special done. Right? Yeah. Well, what value did I have in order to escape this loop? 10. And it retains that value. Done. 10. Right? Yeah, go ahead.
So does it not automatically deallocate that?
It will. I mean, it goes out of scope. It's gone. Right? In fact, let's go ahead and take this over to the
So
see it.
if you declare I on line 14 in your for loop, and then you try and use it outside your for loop on line 17, it'll be undefined.
Undefined. In fact, it won't compile. Right? It didn't.
I see you didn't have a garbage collector.
It doesn't, but it still has variable scoping, and that's what's happening here. Right? So let's visualize this execution. You'll see that. Come on. It takes somewhat a little bit. So I is now born on line 6. It goes through its life cycle, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And it still exists outside that loop over here with value of 10. If I go back and edit this code, and let's go ahead and make sure that it visualizes something int x is equal to, and let's just say that x 42 here, right? So now let's go ahead and get rid of this. All right. So now you'll see that the I dies, it goes out of scope after that loop. So let's go ahead and fast forward here. 1, 2, 3, 4, 5, 6, 7, 8, 9. What's about to happen here? I's gone, right? So it's not garbage. Garbage collection, it deals with the heap and things that are not in the stack. And so this is not really garbage collection. It's just that the compiler, I mean, it's going to be there in memory somewhere in the stack. It's just that it goes out of scope, so the compiler is going to say, if you try to ever use it, I'm not even going to compile on you, or compile for you.
So what stores the heap versus the stack?
So the stack is small but efficient. That when we get to functions, a function will call a function, will call a function, will call a function. These are called stack frames. They store parameters, local variables, etc. Things that are within the scope, in the current scope. The heap is much larger but less efficient, and so if you need, like, I don't know, 50 megabytes, you're going to the heap over here. Good. So yeah, we're in C. It doesn't have objects, so no. Only the things that are on the heap in C are the things that you manually allocate using malloc, memory allocation. In Java, it really depends. I mean, if you go with an array, will be stored in the heap, right? Even if an object array or a primitive array, it doesn't matter. Those will be stored in the heap. But the reference to that thing will be stored in the stack. Yes. Right. So we'll be talking about all that stuff in much more detail later on. Right? All right. So let's take a look at that new syntax. Right. We don't need a big header on that. I plus 1 plus plus adds 1 to the variable I. You can use, and unfortunately I see this all over the place, that is the prepended increment operator. But why? Right? This is the prefix version. Right? The other one is the postfix version. And I see people that just get into the big habit of doing this. And there is a difference between the two. They'll both add 1 to the variable I, but the value of the expression is different. If I was 5 before and now it's 6, either the value of the expression is 6 or the value of the expression was the original 5. I never remember which one, and I never use it in any expression because I can't remember which one. So why? It's just additional syntax that you always have to remember. Does it take on the original value or does it take on the new value when you're using it in an expression? Just don't use it in an expression. Don't bother using the prefix there. Right? You can also have I minus minus. Imagine what that does. Subtracts 1 from I. Right? From I. Right? So new fancy syntax here. You can also have I plus equals 2. Right? This adds 2 to I. Right? Did you see that? That's called a compound assignment operator. Why? I mean, you could write something like this, right? I is equal to I plus 2, right? Or you could get away with some fewer spaces. Okay. Again, this is all syntactic sugar. Right? You can also do, say, times or minus equal, which will subtract. This subtracts 2 from I. You can also do I times equals 2. And 2 is just my go-to, right? This could be 5, it could be 42, it could be 3, whatever. This multiplies by 2 and sets it to I. In other words, it doubles the value of I. Right? Another way of saying that. And then finally, I divided by equals 2 divides, be careful, truncation, right? By 2. So it halves it. Halves it. Truncation. So you have all of those compound assignment operators if you just want to get away with a little bit. Yeah?
What's the difference between doing like I plus equals 2 and then just in the third slot doing I plus 2? Will it not compile if you do it that way?
Ooh, what do you, say this again, so let's do this.
So that third block, that floor of the for statement,
Third block of the for statement?
yeah, for like the increment operator right there.
Yeah. All right. Plus equals 2?
Yeah. What's the difference between that and I plus 2?
If you just go I plus 2, that doesn't do anything. Right? I mean, that will add 2 to, but it won't save it back into I. Right? So let's actually take a look at this. This is interesting. All right? So it's going to go up by 2, so it'll start at 0, of course, like before. Go up to 2, 4, 6, 8. I wonder what it does then. Oops. Got to get rid of this now that I've changed it. All right. All right. 0, 0, 0, 0, 0. Why? Because it didn't save it back into I. I has a value of 0. It is strictly less than 10. I plus 2, but then what do you do with that result? You throw it away. Right? So it never actually changes. It's always at 0. You will get yourself into this situation eventually where you've got an infinite loop. How do you kill it? Control Z. That's what that caret means. Control and then, or sorry, Control C to kill it. Yeah.
Can you show us how to do a for each loop?
In Java we can, but we need collections and we haven't gotten there yet, so I'll preview that. But let's go ahead and take this over to Java for this one, because we do have an infinite loop in Java as well, right? Well, actually, no. Java is going to warn you, not even just warn you about this. It's going to say, no, you can't do that, right? Because you got to do something with that. So plus equals 2, and now it will actually run. There we go. Why didn't it print 10? Well, because 10 is not strictly less than 10. Right? So it goes up by 2's there. If you want to do, you can go up by 3's. What's the last value that's going to be printed there? 0, 3, 6, 9. There we go. All right. So, but what happens if you get into an infinite loop? What I'll do is I'll start this at 100. If I start at 100 and go up by 3's, what will it print? Nothing in this case. Why? Because immediately I'm past this, right? So while I is greater than n, let's change it that way. 100, 103, 106, right? Is it always going to be greater than 10? Yep, so infinite loop. Right. Now, how do you do this? How do you kill it here? Well, you can't use Control Z. If you started it off with the play button, might the stop button do it? Yep. And then you can clear that out. Right, so play, stop. Right. So do be careful. Right? But you're eventually going to have that situation anyway. Right? The other type of loops that we're going to look at are while loops. Right? So a while loop uses the keyword, what do you think? While, exactly. That's what it says on the tin. Right? The main difference is that the three elements, that is the initialization, continuation, and increment, can be are on separate lines. Right? Increment. Don't know why I can't spell today. Okay, so let's go ahead and show you the equivalent while loop here. Int I is equal to 0. There's our increment, or sorry, there's our initialization. We do that before the loop. Then we use the while keyword here and put the continuation condition inside parentheses just like before. While I is less than n, here I've got n is 10. Printf I is equal to %d and the line I. Right. So while I is less than n, and you can space these things out a little bit more if you want to. That's a little bit too much space for me. So I will do it like this, but I do like to put spaces around the less than, right? Again, just be consistent about it. If you don't like spaces, fine. If you do like spaces, if you really like spaces to the point that you're going to put spaces everywhere, then fine, but be consistent about it. Now there is a problem here. I see an initialization, I see a continuation, but do you see the increment? No. So let's put that in. Usually the increment is at the end of the loop, so I will do that. I will do the same as well. It's at the bottom of the loop. Right? Let's take a look and see what that looks like over here in, I don't know, C. There we go. And tab that over. Now you tell me, what's it? Come on. Come on, there we go. And space that over as well. All right, DCC that, and let's run this. It's going to be exactly as before. It starts at 0, prints 0. It goes up to 9, and then it's done. But the thing about a while loop is that it's a little bit more flexible. You didn't have to put that at the end of the loop. You could have put it at the top of the loop. How is that going to change the behavior, though? I is 0. 0 is less than 10, so it'll execute. Now what is it? It's 0 before, now what is it? 1. And so what gets printed first? 1. 2, 3, 4, 5, 6, 7, 8, 9. 9 gets printed, I believe. Then we come back up here. 9 is strictly less than 10. Is that true?
Yeah.
Right? So what does it become? 10, and it ends up printing 10 as well. So it ends up going from 1 up to 10 instead, because of our placement of the increment here. But while loops are usually used to when you want more flexibility, right? If there's some really weird condition, like I'm going to break out of that loop or something like that, I don't cover the break keyword, but you probably will see it in your reading or whatever. You can actually break out of it. Break, right? Break ignores everything, and once you get to it, immediately jumps out of this loop. So let me show you this. What's it going to print? Nothing except for the done. Why? Because we come in, I is 0, so I++, now it's 1. We break, we jump immediately out of the loop. Break out of the loop, that's what that's doing, right? This is a very, very old style syntax called goto, kind of. You jump to this location in your code, jump to that location in your code, and pretty soon you've got spaghetti code everywhere, which is why I don't generally cover the break keyword, right? Instead, rethink your logic, reformulate your loop so that it's correct logic, right? That's much cleaner. Right? DCC that, and we're back to 0 through 9. Okay? All right, so another thing to observe about this is that can you scope that index variable or that increment variable to the while loop? While int I equals 0? Something like that. Well, if you want to do that, you're shopping for you're halfway to a for loop anyway. You might as well just use a for loop. But it's not even going to compile in this case, right? Because you cannot declare and scope the index variable right there. Consequently, because you are forced to scope that variable outside of the loop, it exists after the loop as well. Printf I is equal to %d and the line of I, and we can see that it exists, it lives outside that loop, after that loop, and it takes on whatever terminating value it had. Okay? So, those observations. It's a little bit more flexible. You can place the increment statement anywhere inside the loop, right? Or not at all. Because if you don't put one there, you're going to have an infinite loop, and you'll have to kill it with Control-C, or the stop button. You cannot scope a counter or increment variable to restrict it to the while loop, right? Because it must be declared before the while loop. Consequently, you've got larger scope on everything. And again, in general, it's best practice to limit the scope as much as possible. So if you have a choice between a for loop and a while loop, probably want to go with a while loop because you can scope that variable just to to a for loop because you can scope that variable just to the for loop. In fact, you can do it multiple times. Let's go over here to Java since it'll be easier. Undo. 0, I++, right? There we go. And let's go ahead and do this twice, right? There are two variables that I've declared called I, right? Well, that's okay because one is scoped to this for loop, one is scoped to this for loop. And so I'm just repeating this twice now. Right? 0 through 9, then 0 through 9 again. Right? But because it's scoped to just this loop, you know, you're restricting the scope, and that's the best practice. So to end this today, and we'll get plenty more practice later on, why 2? Why? Well, in fact, there are also do while loops, and there are also enhanced for loops or for each loops in Java. So for loops, why? Why use for loops when one do, right? One will do, right? Well, any while loop could be rewritten as a for loop and vice versa. Right? We just saw that. You can take any loop and translate it into the other loop with some with very minimal changes, right? So why multiple loops? Right? Well, in our regular language, why do we have many synonyms that mean the same thing, right? For example, today is a good day. Today is a nice day. Today is a lovely day, right? We like our language to be rich. We like a lot of adjectives to describe things because it gives context. It gives additional meaning that we can communicate to each other. Well, we like flexibility, right? We like flexibility in languages, right? We like them to be expressive, right? In code, this is syntactic sugar, right? So we like our language to be flowery. We like our code to be sugary, right? Because it tastes better, right? If you're forced to read code all day or something, you like it to be at least a little bit sugary because otherwise it's just bland, right? So we do like syntactic sugar. In fact, one example here was this added syntax. These compound assignment operators and these increment and decrement operators, they give you another way of writing it that's a little bit more terse, and because it's shorter, it's easier to read once you understand what it means. We like our loops because, one can be used in one situation that is more appropriate versus another that can be used in another situation. And for that, I'm going to give us an exercise here. Right? So, int, let's go ahead and get rid of all of this. Right? Int, and I'm going to go ahead and leave this as question mark, right? So what I'm going to do is I'm going to compute the number of digits in, let me rename this to x, in the integer x. Now, if I just hard-coded this, you can, as a human, you can look at this and you can tell me right away. There are 3 digits there. There are 4 digits there. There are 5 digits there. There is 1 digit there. There is still 1 digit there. Right? There is 3 digits there. The sign doesn't count. Right? But we have to communicate and tell a computer how to do that. Right? So, how do we? Ideas. Okay, so let's go with an example here first because we're going to, the whiteboard is over here, but it doesn't show up on an example. Once you've worked it out with one example, you can generalize that so that you can write code for any example, right? Normally, you'd write it up on a whiteboard and no, that idea doesn't work, cross that out, erase that. Once you've got an idea that works, then now you come over to code, but I'm going to do it all in code. So 123, your suggestion was to divide that by 10. What would that give me? 12.3. Relying on integer truncation would get rid of the 3, right? Divided it by 10 again, keep on your hand here how many times you divided by 10. Right? Once. Divide by 10 again. Truncation throws that away. I did it now twice. Divide it by 10 again. Integer truncation reaches 0. I did it thrice. Right? 1, 2, 3 in there. Can I do that with a for loop? I could somehow, right? But is it natural to do that with a for loop? Because with a for loop, for I equals 0, I is less than 10, you know that you're going to go 10 times. But do I know how many times I'm going to be doing that division? Nope. If I knew that up front, then I'd already have the problem solved. So let's use a while loop. Oops, not x, but 1, 2, 3. Let's go with that example there in order to understand it. Right? We might have to fix our code here. But I'm going to go ahead and go into a while loop here. Right? And the thing I'm going to do is what you suggested. X is equal to x divided by 10. Is there a more compact way of writing that now that we've learned compound assignment operators? Divides equal by 10. It's not equals divided by 10 because that's divide equals by 10. Okay. What's my terminating condition here? 123, then it goes to 12, then it goes to 1, then it went to 0 and I stopped.
You can't do that.
While x is greater than 0? Okay.
X isn't 0. So
Or not 0. Okay, what you're looking ahead to what?
negatives.
Negatives. Right? 123 divided by 10. Right? If I go, will I do any division there at all if it's negative? Nope. So while it's not equal to 0. Okay.
But then if your integer was 0, you would get nothing.
Exactly. So you're good. You're whiteboarding these things, throwing up problems. So if I were actually writing, I would put down, what about 0, right? And so we'll come back to that. That's one of those corner cases, one of those edge cases that you have to think about with respect to loops and with respect to testing. But I'm going to go ahead and divide by 10 there. Right? Now, remember over on my hand over here, I was divided it once, twice, thrice. So I probably want to counter there as well. Int count equal, or it represents what? 1, 2, 3 digits in 123. So num digits. What should I initialize it? Or just leave it?
No.
Oh, what value does it have right now in C?
0.
Dead beef, who knows? Right? So let's make it 0 explicitly. Probably 0, 99 times out of 100, but who knows? Right? Although those of you that are using Windows and VS Code are finding out really quickly that it's 32,138 or something like that. Some weird numbers. That's dead beef. Yeah.
So about like if you want x to be equal to 0 and you want to divide by it, then could you not just make it greater than or equal to 0 and then the 0 will also go in?
Like this, greater than or equal to?
Yeah.
What happens when I go negative? I still want to know how many digits there are. So I will never end up executing this while loop here. Right? So if you had if you hadn't given the spoiler, I would have run it and then we would have seen that it wouldn't have worked. But you looked ahead already. Right? So num digits plus plus. Right? So let's walk through this. It's 123. It's greater than or equal to 0. Or actually, I said greater than, right? Not equal was the original. There we go. Right? 123. Right? Num digits is 0 here. Divide by 10. It's now 12. Num digits plus 1. Now it's 1. Num digits plus 1. Now it's 0 num digits plus 1. But then do we end up executing this? Nope. So printf %d has %d digits. Let's see if this worked. And the thing I'm doing is x and num digits.
But x won't be the original.
Yeah, good. Good observation there. X is now changed. Right? So let's go ahead and create a copy of it so that we have the original value. Original is equal to 123. And then I can say that x is equal to original. And then I will manipulate x there instead of the original. And so let's go ahead and print out the original. All right. Oops. Clear. I can't do it twice. That's why. There we go. All right. Has 3 digits. Cool. Now you were looking ahead already. Negative 123. Is that going to work? 3 digits. 4, 5, 6, 7. Should still work, right? 7 digits. All right. So what probably doesn't work? 0. 0 has 0 digits. Those are one of those edge cases, right? How can I incorporate that into this loop? Well, you could do some mental gymnastics and make the loop way more complicated than it needs to be for 99.999% of all the cases, or you could do something else. Yeah.
Yeah,
If original is 0, then printf hardcode it. 0 has 1 digit. There we go. Yeah, so else all the rest of this stuff. There we go. There, 0 has 1 digit. Now make sure you didn't break anything. Those are called regressions, right? You regress, instead of progress, forward, making progress and improvements, you are regressing, and maybe we broke 123 by doing this stuff. Nope, it still has 3 digits, right? And this is why you start writing unit tests like you did yesterday in your lab for is leap year, right? Now, those were informal ad hoc unit tests. We're gonna eventually look at formal unit testing. Yeah.
For the lab and the hack, do we have to keep those unit tests in?
I forget. If you got your 15, you got your 15. No, hack.
For the hack, though.
Oh, the hack. We're just on informal unit tests. So you're holding your calculator off to the side, and is that the correct error distance? Okay, yeah, it looks like it, or whatever. You're on a piece of paper is what we're looking for there.
Like in hack free, it says to keep your, do we have to keep our unit tests in?
No. I mean, you can't, because we haven't shown you how to write unit tests yet.
But not like commented out.
Oh, yeah, if you get rid of that, that's cruft, yeah. We probably won't take off for it, but we'll say don't leave that in there. Generally, when you do actual unit tests, they're completely separate pieces of code. You don't want your tests and your code coexisting like this, right?
It just says to write some unit tests, so I didn't know if you had like print statements and wanted us to leave it.
No. What we mean is, here's my input up on a board. Here's my output, my expected output.
No, it just says.
And then you run your program and you say, oh, okay, it works.
It just says to make free, so I didn't know that.
Yeah, not formally yet. Right. So, all right. So again, why a while loop in this case? Well, because we don't know up front how many iterations we're going to go. And that's generally the difference between the two. I'll go ahead and leave this in the notes so that you have it. But, while loops are generally used when you don't know how many iterations. Oh, come on, am I not? Oh, I'm not in the code mode, sorry. I didn't get out of code mode there. There. While loops are generally used when you don't know how many iterations you are going to execute, right? For loops are when you do know upfront, a priori. There we go. Nice Latin. That's how you spell it, right? A priori, upfront, upfront. Let's not be fancy today. How many iterations you're going to execute. Even if it is a variable n. I'm going to execute this for n iterations. Well, then just use a for loop, right? It's more natural, right? Now again, do you have to do one or the other? No. But there are certain situations in which you'll naturally want to do one or the other. Right? Okay, 5 minutes here. Consider the following. Let's fix this, and then we'll look at some other pitfalls when we come back on Friday. What's wrong with it?
The semicolon.
Yeah, another extraneous semicolon. What happened when we did this with the if statement? If this was nothing. While I is strictly less than 10 or less than equal to 10, do what? Nothing. What's going to happen? Yeah, run forever. Why? It never changes I. Right. There we go. It's not even printing. Actually, why is it not printing? Oh yeah, why it's not? It's stuck right here. Stuck right here. Right. Right. This is not bound to the while loop down here. So we kill it with Control C. Right.
If you use dash wall for that, do you think it'll let you know?
Hopefully, it should be smart enough. Yep. Yay. Warning. While clause does not guard there. Are you sure that you meant to do that with that semicolon there? Right. It can find common, easy mistakes like this. Right. It cannot solve everything. In fact, there are mathematical proofs that show you cannot write a program that will test and evaluate another program to say, nope, you're going to get stuck in an infinite loop there. Right? No such program exists. It's called the halting problem, and it gets into self-reference and strange loops and stuff like that, way beyond the scope of this course. But for most of the practical cases, you can rely on your linter. Right? Remember, you're picking the lint off of your code because it's not necessarily dirty, but it's something that you probably should not have there. Right? The problem here is the extraneous semicolon. So the semicolon is misplaced. It results in an infinite loop. And just to remind you that a Control C will kill a running program. Use proper wall flags to catch these things. Yay. And in Eclipse, you have a stop button. All right. I guess we could do one more. What's wrong with that?
You don't include.
Yep, we already saw this one, right? We never, we didn't increment it, and so it always ends up printing, in this case, 0. Oh, yeah, 0, because we started at 0. Right. All right, and the last one I'll show you, and then we'll figure it out next time. No spoilers, please. All right, if you know what's wrong there, then you can tell me immediately when we get back. Now, if you come from a Python background, nothing looks wrong, right? So we'll talk about that on Friday.